Okay, well, welcome back let me show you my title, Calculus Conundrums Limits by the Perfect Square, and feel free to subscribe. You can always use more members. Okay, so the existence theorem for limits basically works like this. If f is a function and c and l are real numbers, then the limit of f of x as x approaches c equals L if and only if the limit of f of x as x approaches c from the left is L and the limit of f of x as x approaches c from the right is L. So basically what that says is that if this is true, then both of these guys are true. But since it's if and only if, it also goes the other way. If both of these guys are true, then this is true. Okay? So let me just kind of show you. In an earlier example, we showed that the limit of x cubed minus 1 over x minus 1 as x approaches 1 is actually 3. Well, if that's true, then we also know from this theorem that the limit of that same function as x approaches 1 from the left must be 3, and the limit of that same function as x approaches 1 from the right is 3, because that's what that says. Now, let me show you another thing. Earlier, we showed that the limit of this function as x approaches 1 from the left, I think we showed this was negative 1, and the limit of this function as x approaches 1 from the right is positive 1, so they're not equal. So in this case, since the left-hand limit does not equal the right-hand limit, then we know from this theorem, since this would not be true, since these two limits would not be the same, then we know the limit itself would not exist. Okay, so that's really how you can use that existence theorem. Okay, now I want to look at some more examples of limits. Another area where we can look at one-sided limits are piecewise functions. So let me look at a couple of piecewise functions here. Here we have a function that says we have 2x minus 1 if x is less than 3, and we have x squared minus 4 if x is greater than or equal to 3. And we want to find the limit of this function as x approaches 3. Okay, well, let me show you something here. Let me show you, I can show you this better if I graph. Okay, let me show you what you're looking at. I went ahead and just drew a dotted line here for x equal 3. That way you can see x equal 3, because that's where the graph changes. So to the left of 3 we get 2x minus 1, and to the right of 3 we get x squared minus 4. So I went ahead and graphed, and on Desmos you can actually do this. I went ahead and graphed y equal 2x minus 1, but only for x is less than 3. And that's this blue graph right here. Alright? And then I graphed x squared minus 4, but only the portion where x is greater than or equal to 3. Okay? Now let me go ahead and take that vertical line out. So that's what the graph would look like. The blue is the linear function, and then the green is the quadratic function. Now these appear to hook up, but here's the deal. Let me turn that 3 back on. So if you find the limit of this piecewise function as x approaches 3 from the left, well, the limit as x approaches 3 from the left, you could just plug that in to the function on the left, and that's going to give you 5. So you could plug 3 into that because that's the function on the left, so to the left of 3. So as x approaches 3 from the left, you'll be coming in on this function, and so 2 times 3 minus 1 is 5. But if you find the limit of this piecewise function as x approaches 3 from the right, you're coming in on the quadratic function. And so you would plug it in here. 3 squared minus 4 would be 5. Now fortunately they're both the same value. So what does that tell us? Well, since the limit as x approaches 3 from the left is 5, and the limit as x approaches 3 from the right is 5, and these two limits are equal. Okay, that should be a plus. Okay, and these two limits are equal, so since both the one-sided limits yield the same value, then the two-sided limit, or the limit itself, exists, and it must also equal 5 due to the existence theorem that we just covered. Alright? Now let me show you this next one. Let me go ahead and graph this next one, and I'll show you that one as well. I tell you what, I don't really need to graph this one to work it. I didn't need to graph this one to work it, actually. So let me show you how you can work it without actually graphing it. Now you know if x is less than 2, you'll get this function here, right? And if x is greater than 2, you'll get, now I didn't catch my little thing here. Alright, there we go. So you'll get this function. Okay, so if you want the limit of x, if you want the limit of this function as x approaches 2 from the left, you actually would be looking at this function. So you'd have to plug 2 into this function and get 2 minus 1, which is 1. Okay? Now, but if you want the limit as x approaches 2 from the right, you'd plug into this function. And if you plug into this function, you get 2 squared minus 1, which is 3. And now, since both one-sided limits exist but equal different values, then the two-sided limit does not exist. I don't know where that came from. That's not supposed to be there. Well, I do know where it came from. I did a copy and paste. So anyway, the limit itself does not exist. So the limit of this function as x approaches 2 does not exist. Now, I'm just going to wrap this up with a little bit of common sense. When the numerator approaches a constant other than 0 and the denominator approaches 0, then the limit must be either increasing or decreasing without bound. In other words, the limit is either infinity or negative infinity. Once this is determined, that should say once this is determined, you can do a small amount of investigation to determine whether the limit is plus infinity or minus infinity. So here it says, find the one-sided limits. Well, we know that as x approaches 1, this is going to become a constant. 1 plus 3 is 4. But as x approaches 1 down here, this is going to go to 0. So this limit must go to infinity or negative infinity. Same thing for this right-hand limit. It must go to infinity or negative infinity. So all I have to do is find a number that's just slightly less than 1. So let's pick a number that's real close to 1 but less than 1. How about 0.99? So plug 0.99 in here. So you would say 0.99 plus 3 divided by 1 minus 0.99. And I got 399 with that. Well, since that's a positive number, then this limit must be positive infinity. So this limit's positive infinity. Now, here I want the limit as x approaches 1 from the right. So I pick a number just to the right of 1, like 1.01, and I plug that in here. So I got 1.01 plus 3 divided by 1 minus 1.01, and it gave me a negative number, negative 401. So I know that this limit must go to negative infinity. See, I already knew it went to one of the infinity sisters. I just didn't know which one. So once I picked a number that represented a number close to 1 to the left or close to 1 to the right, then I could determine which one of the infinities it goes to. Alright? Now, we're going to look at this again a little bit later, but we're going to talk about limits as x approaches infinity or negative infinity later. But here's what you can do for now. Let's say you want to know the limit of x plus 3 over 1 minus x as x approaches negative infinity. Well, what you could do is you could evaluate this function at a very, very large negative number. And let me show you that. Okay, so this is my function, x plus 3 over 1 minus x. And since I wanted to get some idea of where this function is headed as x goes to negative infinity, notice I just chose a very large negative number. And so I'm just going to evaluate this function at negative 10,000. Well, notice when I do that, I get negative 0.9996. Now, if I went farther out, then it gets closer and closer. So actually it gets closer and closer to -1. So the farther negative that I go, the closer this gets to -1. So I'm probably safe by saying that the limit of this function, as x goes to -infinity, is -1. Now, it's also true if I let x go to +infinity. So notice if I let x go to +infinity, see that's a very, very large number, 10 million. Notice it gave me -1.00000004, which is basically -1. So actually, you can see there that we get values closer to -1. Now we're going to learn some shortcuts for limits as x approaches infinity or -infinity later when we get into horizontal asymptotes. Now, speaking of asymptotes, what I want to go back and show you, remember we ran into some problems where we were getting infinity and -infinity when we did these one-sided limits. Well, that leads us into vertical asymptotes. So I'm going to show you how to identify vertical asymptotes in the next video. And vertical asymptotes are related to the functions that you have when you let x approach a number and you get infinity or -infinity.